So the last test I'm going to talk about shows you how to evaluate relationships between categorical variables. So this would be if you had variables that weren't interval ratio level, that were ordinal or that were nominal, you could do a chi-square test. And you see this a lot in the literature, so I wanted to make sure that we talked about it. And what a chi-square does is it looks at what we expect the frequencies to be of the different cells, and then what we actually observe, and compares those. It requires independence, and it requires the expected counts are greater than 1. So I'll show you what that means, and that no more than 20% of the cells are less than 5. And if that assumption, if those assumptions aren't met, if the chi-square assumptions aren't met, so if you have an expected count that's 1, or if you have some cells that are 5 or less, then you could switch and use the Fisher's exact test instead. So an example of when you'd use a chi-square is if a researcher wanted to study whether there was a relationship between the type of school that someone attends, so public versus private, and the student's gender, so male versus female. So you have two nominal level data. You have categorical schools, public, private, and then you have gender, male, female, and there's no order to them. And so you couldn't run like a correlation between those two because they're two categorical grouped nominal data. So instead we'd look at a chi-square. So we want to develop a null and a research hypothesis. And our null hypothesis would be that there will be no relationship between the type of school attended and gender. And our research hypothesis would be that there will be a relationship between the type of school attended and the gender. We'll choose our level of significance and what statistical test is appropriate. We're going to choose a 0.05, and we're choosing the chi-squared initially because we know we have nominal level data, so we can't look at a relationship between two variables through a correlation if they're nominal. So our only option is chi-squared, but then we know that if our expected counts are less than 1, or if there's more than 20% of the cells where they're less than 5, we're going to switch and do a Fisher exact test instead. So we're planning to do a chi-square, but we know we need to make sure that assumption was met. And we're going to run our analysis and obtain our test statistic and our p-value. So this first table gives you what I was talking about with your cells. So this is kind of imagine like a 2x2 table, and if we have one of our variables across the rows, which is our type of school. So public is the top row and private is the bottom row or the middle row, and then we have our totals at the bottom. And then gender, so male is our left-hand column and female is our right-hand. So we have 44 males that attend public school and 14 that attend private school, and 91 females that attend public school and 18 that attend private school. So in total, 168 people attend public and 32 attend private. Looks like they looked at a total of 200 people, 109 of which were female and 91 that were male. And so when we look at this, none of our cells, our 77, our 91, our 14, our 18, those are our actuals, but none of those are small enough numbers that we would be expecting less than 5 in one of them, or anything would be 1. So we're really able to run a chi-square, and we don't have to worry about switching to the Fisher exact test because our numbers are big enough. Our next table that comes out with SPSS gives you your chi-square. So you look at that very first line, and the way you write chi-squared is it's kind of the italicized X, I don't know the name for it, but squared, and then in parentheses your degrees of freedom. So remember we have two groups, so type of school has two groups, public, private, and gender has two groups, male, female. So we take our number of groups, 2 minus 1, and we get our degrees of freedom. So 1 equals 0.047, and then if you keep going across, you'll see our p-value is 0.828. If you look about 4 rows down, it says Fisher's exact test. So if it had come out that one of our cells was really small, we only expected 1 or 2 people in it, then we would ignore that top Pearson chi-square and we choose to report the Fisher exact p-value in either one-sided or two-sided based on whether our research hypothesis is non-directional, meaning we'd use a two-sided test, or it was directional and then we'd use the one-sided test. But as you can see in the bottom of this output, it tells you that 0 cells, so 0%, have an expected count less than 5, and the minimum expected count was 14. So we don't have more than 20 with an expected count less than 5, and we don't have any, the minimum, we don't have any at 1. So that tells us we're fine using the chi-squared. But if we looked at that little thing under and it had given us, 30% had expected counts less than 5, then I'd choose to report the Fisher's exact test instead. Next, we'll make a decision. So our p-value is 0.828, which is greater than our level of significance that we set. So remember, whenever our calculated p-value is greater than our level of significance, we fail to reject the null. Our null was that there will be no relationship between type of school attended and gender. So if we're not throwing that out, then we're agreeing with that. And we'll make our conclusion. There is not a statistically significant relationship between the type of school attended and gender. And then we report our chi-square and our p-value. And that is it for our non-parametric tests in this module. And so, like I said, there's a few extra ones in your text, but you aren't required to know those for the test. But if you are reading an article or something and it has one of those, feel free to research the additional ones. But I think I've covered the ones that you see most commonly in the literature.